The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the second in our series of AI/ML talks. These are co-sponsored by George Mason University and Metron. And as well as the talk today on deep learning, a Bayesian perspective, we also have scheduled 4 additional talks. And I'll just give you the quick times and titles. I'll send these out to you in notice so you can plan ahead. But there'll be a big gap here, but July 30th, we have a talk by Alexander Bayan at the University of California, Berkeley, on global vehicle control at large and local scales with mixed autonomy traffic, optimization, and deep reinforcement learning approaches. On August 6th, we have probably a very controversial talk by Dimitris Bertsimis, the MIT Sloan School. This is optimal classification trees and interpretable AI. So interpretable and explainable AI, that's a big deal. August 13th, Nicholas Polson, University of Chicago, sparse Bayesian regression for high-dimensional regression and classification. And September 18th, Yana Koseka from George Mason University, AI for detection and identification. So today, I'm going to give you a little background on Vadim here, who is a professor at the Systems Engineering Operations Research Department at George Mason. He works on building robust solutions for large-scale, complex systems analysis at the interface of simulation-based modeling and statistics. This involves developing new methodologies that rely on deep learning, Bayesian analysis, and design of computational experiments. So inspired by an interest in urban systems, he co-developed a mobility simulator called Polaris that is currently used for large-scale transportation networks analysis by both local and federal governments. Prior to joining GMU, he was a principal computational scientist at Argonne National Laboratory, a fellow at the Computation Institute at the University of Chicago, and a lecturer at the Master of Science Analytics program at the University of Chicago. Professor Sokolov.
Thank you very much, Larry, for organizing and inviting. And I had a chance to meet several people from Metron. It looks like you guys are doing quite amazing stuff here, and hopefully something will grow out of the seminar series and collaboration between you and academia. Bayesian perspective from deep learning, just to give you highlights. I don't think I have any good answers for you in terms of how to bring Bayesian in deep learning. I don't think there are good ways so far to do it. And we just talked about those big companies paying a lot of attention to deep learning. And it doesn't seem like they pay too much attention to Bayesian aspects of deep learning. If you see a lot of the papers come, they don't have much of Bayesian flavors to it. And people who do Bayesian inside of Googles and Facebooks, you basically can count them using one hand. So there's not that much happening in this area. So I think there's a lot of work to be done. It's an exciting area. So if you're in this Bayesian deep learning interface, I think there's still. I mean, field is very competitive because it's very competitive field. It's hard to come up with something new, but this interface between Bayesian and deep learning, I think, has a lot of potential for development. The work I'm going to present, a lot of it is published in Bayesian Analysis Journal. It's a 2017 paper. It has the same title as the title of the presentation. It's a survey paper that was written for statisticians. We try to explain what deep learning is and how deep learning can be interpreted from Bayesian perspective and from statistical perspective, and try to connect, deep learning to non-parametric modeling, for example. So it was our attempt to explain to statistics community what deep learning is, and there's not much, I think, happening in statistics. Also, I think statisticians are still picking up on deep learning. If you I go to stats conferences a lot, and you barely see any deep learning talks at stats conferences for some reason. But I think this thing will slowly be changing. It just takes a while for stats community to adapt. And this is another paper that has some of the beats of the talk. It's actually to be published soon. This is basically spatial temporal modeling and how we can use deep learning in spatial temporal modeling. Spatial temporal modeling is classical application in statistics, and we showed that deep learning methods can outperform more traditional statistical tools and we showed for high frequency trading and traffic flows. We showed for two applications. That's how we started working on deep learning. We started, my applications were in transportation. I worked with Argon, and a lot of the work was around transportation. And it seems like it's second transportation talk, and you're going to have Alex Ban's going to be talking. So you'll see some transportation applications here, but nothing wrong. It's it's a fruitful area. And one of the quintessential transportation problems is to predict traffic flows. Okay, and traffic flows can be predicted using the observations. So we have observed data. The red dots are the sensor locations. We collect vehicle speeds, volumes. Basically counts how many vehicles go through this location. We have 1,500 of them in the Chicago metropolitan area, so we collect this data, and we want to predict speed in the next 45 minutes given the current speed and the speed observed for the last 24 hours. We were particularly interested in predicting non-recurrent events. It's somewhat of an easy problem to predict recurrent events. So you know that 66 is going to get congested at this specific time, at this specific location. It happens pretty much every day. Can we say something about non-recurrent events? So this is an example of the various gains. So the red line is your average speed at this specific location of I-55. That's a highway that goes from south suburbs to the downtown Chicago, where the Bears play their games. And so the red is the averages. This is your normal day. And the blue line is the day when Chicago Bears were playing, and you can see that there's deviation between 3 and 8. The game starts at 7, I believe, so traffic starts around 3 p.m. So there's a huge deviation, and our goal was to try to predict those things. So rather than predicting normal traffic patterns, we want to predict those outlines. I'm not going to go through methodology, and okay, so there's another example. There's a whole bunch of non-recurrent events, right? So sports game is one of them. Weather event is another one. This is January 21st, 2016. This is Washington, D.C., and the snapshot was taken at 12:41 a.m. So this is almost, it's 40 minutes after midnight. On a normal day, you won't see any traffic in this area, but you see a complete gridlock at 1 a.m., okay? And the reason for this complete gridlock is snow, and we're talking about half an inch of snow as far as I remember. So it's a very minor weather event, compared to big hurricanes, for example. It's a very minor event that can disrupt the whole system and put complete gridlock. So relationship, the spatial temporal relationship in traffic are very nonlinear. This is example of the speeds, and this is in meters per second, so 25 meters per second. To get to miles per hour, you need to roughly double it. So it's roughly 50 miles per hour. So this is the sensor 6040, and this is sensor also 6040 with some time delay. So basically what you see is at time t and the time t plus 10, and t is time step is 5 minutes. So we're talking about each observation is here 50 minutes apart from each other. So you see it's very nonlinear. So if you try to use any type of ARIMA model that assumes linear relationship between t and t plus h, this model does somewhat okay, but very inaccurate. And traditional approach was using ARIMA models in transportation. People tried it; it was a workhorse for traffic flow predictions. So we tried deep learning. Not sure if you can see very well. So the black line here is the actual data, and the red line is the prediction by a deep learning model. And this is a prediction, so this is a noisy prediction, so we actually can ignore the bottom row, we can just focus on the top row. So the red line is the prediction that comes out of the deep learning model. An important part of it is that, so here where surprise is happening, so you remember on a normal day, we didn't see this congestion here at around 3 p.m., but the model does capture this degradation. It does predict that there's going to be a downgrade in the traffic flows. And then when recovery starts, it's also quite accurately captures. It's actually anticipated a little bit early, so the recovery will start a little early, see this bump here. But then it captured this recovery and predicted it. So I do not show you a ARIMA prediction, but the ARIMA prediction is going to be way off in this situation. Okay? So a deep learning model was able to capture the spatial relationship, spatial temporal relationship in the traffic, and was able, so this is weather day, this is snow, and this is normal day. And normal day, it's actually almost perfect fit. Just because in normal day, there's a lot of patterns in the data, and deep learning picks up those patterns quite well. And normal day is actually quite an easy task for deep learning to predict. Okay. So why do we care about deep learning? This is mostly for people who have not worked with deep learning models, who are still in the phase where trying to figure out what it is. So I have a quick overview. Deep learning is a pattern matching algorithm that works very well in high-dimensional spaces. Most of the successful stories of deep learning that we see nowadays is in natural language processing and in image processing, and those are high-dimensional inputs. So if you think of 1 megapixel image, it has 1 million inputs. Okay, so if you think of traditional statistical model trying to work on 1 million dimensions, you probably won't be able to build a traditional statistical model in these dimensions. So deep learning works. It does quite well. Has a lot of successes. So you had a talk in April from Uber, and there was a lot of applications where images from cameras from cars were analyzed using deep learning. So I have an example of the Waymo, which is a competitor. So Waymo claims they process 6 megabytes of data per second that comes from their sensors, and most of the processing comes through deep learning. Okay, so if you're training more traditional statistics, you can think of deep learning as a factor model, but it's a multi-layer factor model. So factor is a combination of the inputs, right? So in this case, this is a very silly example. You have inputs which are attributes of the house, and you want to predict the price of the house. And rather than building predictive model using the original set of inputs, you build predictive model using the set of factors, which is just combinations of the original inputs. And that's exactly what deep learning does. It does bind those, in machine learning, they call them features or representations. So you take original data set and find features or representations, and you do it multiple times. You do it layer after layer after layer before you get something where, a linear model, for example, a generalized linear model can find a pattern. And at the last layer, you would have generalized linear model. So why deep learning works? It works just because it has much more flexible way of splitting the input space into subspaces and find pattern in those subspaces. This is an example of what tree model does. Tree model, you can think of a tree model as a kernel-based model, or you can, kernel-based machines. Any kernel-based modeling, what it does, it basically builds a kernel. You give a point, and the kernel machine will try to find the neighbors, and then the weights which will be used for the neighbors will be defined by the kernel, and then you average it, and that becomes your prediction. So this is kernel defined by tree model, kernel defined by a random forest model. And what happens in high-dimensional spaces, so why do we need something more flexible than these kernel machines in high-dimensional spaces? You have what is called concentration of measure. And you have concentration of measure as your dimensionality goes up. Here's a very simple experiment that demonstrates the concentration of measure. What I did, I took the two-dimensional image of 1,000-dimensional uniform sample inside the ball. So I take a 1,000-dimensional ball, and I generate samples inside this 1,000-dimensional ball uniformly. So if you basically look at this 1,000-dimensional ball, you'll see uniformly filled samples inside this ball. And then what I do, I take this 1,000-dimensional ball and samples inside of it, and I project it to 2 dimensions. And so what you see is the projection in 2 dimensions. And you see what happens to the uniform sample in 2 dimensions? You basically have a lot of the concentration around the center, just because most of the volume of this 1,000-dimensional ball is around the equator, okay? And most of the, if it's uniform sample, most of the samples will concentrate around the equators. And this is marginal distribution. So if I project it to 1-dimensional space and I plot the density of the samples, so what happens in 400-dimensional space. So that's basically concentration of measures, a function of dimensionality. But that's what happens in 100 dimensions. That's what happens in 400 dimensions. So as the dimensionality goes up, you basically see high and high concentration around the zero. Okay. So if you use any kernel-based technique, what will happen? If I give you a new point here and I'll ask you to predict this is new x, and I ask you to predict new y for this point. Your kernel-based method will try to find neighbors and weight those neighbors to do the prediction. And in high-dimensional space, it's very likely that your new x is going to be very lonely. It's not going to have any neighbors. So your prediction will fail in high dimensions. Okay? So that's basically the problem in high dimensions that is not addressed by traditional stats models. Here's some theoretical justification for why deep learning works. Kolmogorov and Arnold, they showed this result in 1956. They showed that any smooth function, any function, nonlinear, defined on a unit square, can be represented as a superposition of univariate functions. And it's not approximate results, it's actually exact results. So you can show that exactly any nonlinear function can be represented as a superposition of univariate functions. The way they proved the result, they used subtype of fractal theory. So they took a space and basically had this infinite dimension. So it's not a proof that leads to any algorithm, unfortunately. So it's not like you can build this combination of univariate functions, but at least it's a theoretical result that gives you hope that any function, any complex function can be represented as a composition of univariate functions. And that's exactly what deep learning is, right? So that's the definition of deep learning. You have some input space, input x, and you apply some function f to it, and fl-1 up to fl1. And each of those functions is just you take your input, you take a finite transformation to this input. So this is linear plus scalar, and then you apply nonlinearity to it. And if you do it many times, okay, if you do it many times, so that's what deep learning does, it applies it many times, you basically have a very flexible pattern matching machine. And again, those of you who are trained in statistics, you probably recognize this part of the model. So this is linear model, right? It's just the linear model of the inputs. And you apply nonlinearity to linear model, you get what? Generalized linear model. It's just a generalized linear model. So what deep learning is, it's a sequence of generalized linear models applied one after another. So again, from statistical perspective, it's just a hierarchical generalized linear model. There's nothing special about that. Okay, yeah. So statisticians basically, if you take a traditional stats model, it will focus on this, right? Take some nonlinearity and apply it to a fine transformation of your inputs. Deep learning basically takes it and say we're going to do it many times. This is again some silly example of why deep learning works quite well. This is a one-layer deep learning model with ReLU nonlinearity, so that's our sigma function. ReLU is a very simple function. ReLU of z is just max of 0 and z. And what ReLU does, it basically splits your input space with hyperplanes. Okay, and so this is simple ReLU model with 3 neurons, and it splits your input space into 7 regions. And if you start stacking those ReLU layers one after another, you basically will have this exponential growth of the number of subregions which divide the input subspace. So with deep learning, another geometric interpretation of deep learning, you can think of it, you take those hyperplanes, you divide your input space, then you take another set of hyperplanes and you divide those subspaces, and you keep doing that. And as you add your layers, your number of subspaces will grow exponentially. Okay? So that's geometric interpretation. Here's again silly example of we're comparing deep learning models, a very simple neural network, actually, 2-layer neural network with a tree-based model. So we try to discriminate greens from reds. And so if you have some simple pattern, then you can discriminate greens from reds quite easily. This is a tree model, and this is a deep neural network. So, tree model does quite well on the simple pattern. Then you have a little bit more sophisticated pattern where you have, green dots inside the red circle. Again, tree model does that quite well. It basically plots these dividers that goes along the axis. And deep learning does that quite well as well. But the moment you have a little bit more sophisticated pattern, the spiral pattern, right? So you have 2 spirals, one going after another, and you try to build a tree model that fits into that, and of course it fails miserably. It tries to divide the space into those subregions that and line go parallel to the axis, so it doesn't give you any good result. But neural network with somewhat similar complexity, the same depth, will actually will fit this pattern quite well. So it allows you to fit those spiral patterns. Here are a couple of Kolmogorov-Arnold examples. Maybe actually I do have some time. So here a little example of how Kolmogorov-Arnold works. You have a nonlinear function of two variables, x1 times x2, and you can represent it. You remember what Kolmogorov-Arnold said? It's basically affine transformation followed by nonlinearity, right? So you have affine transformation followed by nonlinearity, another affine transformation followed by nonlinearity. Okay, so in statistics you will interaction of x1 and x2, right? So deep learning will represent interaction of x1 and x2 using this representation. Okay, this is another nonlinear function, max of x1 and x2. It's another affine transformation followed by absolute value nonlinearity, affine transformation followed by nonlinearity, absolute value.
Vadim, what's the advantage of that over just x1 times x2?
Because x1 times x2, you basically have to handcraft it. You have to, if you try to build the linear model, and you have to design those features, right? You can do that. If you know exactly what interaction between the terms, you can do that. But the idea of deep learning is that you basically build very complex deep learning model that tries to capture all possible interactions. So, and then you can sparse it out. You can zero out a lot of neurons. So the idea is that you build very complex thing and then sparse it out, okay? Rather than trying to handcraft all possible combinations of interactions. But if you know them up front, if your goal is not to automatically identify them, yes, you can do it by hand. But if you're talking about million-dimensional spaces, doing things by hand, and people spend a lot of years doing things by hand, so a lot of the Bayesian modeling have been used actually. Graphical models we used for image analysis before deep learning was around. And the idea was, yeah, we somehow will try to look, but deep learning looks much better. We can learn computer programs, right? So you have x1 and x2 binary variables. You can find them and operate, and you can learn it as affine transformation followed by nonlinearity. I is the function that returns 0 if the statement is false, and 1 if the statement inside the true. So you can think of I as just nonlinear function. We can learn OR operator. We can use all not operator. So we can learn logical functions using the same concept, affine transformation followed by nonlinearity. So you can think of taking complex computer program and splitting them into logical statements, and you can learn those logical statements. And if you want to have nested statements, like in your program you'll have nested statements, it will correspond to basically layers of neural network. So you have one logical statement followed by another logical statement. It's going to be layer after layer. Okay, so that's basically bottom line. Any function can be represented using deep learning. Two-layer can represent any Boolean function, and any convex polygon can be represented using two-layer network. So you remember those hyperplanes, so you can basically build the hyperplanes and just need 2 layers to have enough hyperplanes to represent any convex polygon. You actually can show that 3 layers is enough to build any non-convex polygon with discontinuities. So just adding another layer allows you to build much more complex geometries. And Kolmogorov-Arnold basically says that affine transformation plus single nonlinear function approximates any smooth function with any accuracy. So this is an example of use of deep learning projects inside Google. They published it. There is actually an updated version of it that goes up to 2016. And that's actually how I first learned about deep learning. I had a lunch with a person from Google somewhere around 2012, and he complained about, oh, everybody has to do deep learning now. I don't know what it is. I don't like it, but we were told that everybody has to try it now. And that was Google's policy then, and apparently it worked. So you can see the number of projects growing exponentially inside Google. Google is trying basically, anytime you dictate something in your Google phone, you take a picture, it will go through a deep learning model nowadays. So they do it at huge scales and do it quite successfully. This is another silly metric of popularity of those models. This is Google Trends. You're familiar with Google Trends. You basically type a term and it shows you the popularity of this term. So this is the regression analysis is the red line, and deep learning is the blue line. And you see what happens at around, March of 2016, a couple of years ago. It basically bypassed. You see this cyclic pattern in linear regression. You guys have a good explanation for cyclic patterns in linear regression searches?
When the academic finals are coming up.
Yes, yeah, twice a year, students realize that they need to take exam. And modern version of, so you actually, it's very good thing. Yeah, modern version of, preparing for exams is don't go into Google and search for the terms that you think you'll be asked about in your exam, and trying to learn from, from Google results about that. Yeah, nobody reads books, by the way, anymore. Doesn't realize people don't like books. Everybody goes to Google and just searches on Google whatever they want to learn. Yeah. By the way, you start seeing cyclic patterns in deep learning. You start seeing cyclic patterns in the deep learning searches. You know why?
Same reason?
Yeah, because it's been, schools started offering deep learning courses now. Yeah. So, I'm teaching deep learning course at George Mason now. So you'll see the same at the end of each semester, students try to figure out. Okay, well, the training and validation is basically you train deep learning model as you would train any other machine learning model. You have to formulate the loss function, and your loss function will depend whether you solve classification or regression problem, right? And you try to minimize the weights and bias terms of your deep learning model. So as basically, in the regression case, you try to minimize the misfeed, the difference between the predicted values and the actual observed values. So there's nothing special about it. But what's special actually about this function? So we have to solve this minimization problem somehow, right? This is a very complex function. So it's a superposition of those affine plus nonlinear, and you have dozens of those layers, and each layer will have dozens of neurons. So it's a quite complex function, and now we have to. Of course it's nonlinear. Function is nonlinear. It's moreover it's non-convex. Okay, and we have to optimize this nonlinear non-convex function somehow. And one of the breakthroughs in deep learning was the realization that simple stochastic gradient descent methods actually work quite well. So gradient descent is the method on stochastic gradient descent is the stochastic version, which comes from Robbins-Monroe. This is 50s. Okay, this is technology from 50s. Nothing new about that. At some point, people realized it works quite well to minimize those functions, and it actually happened, in late 90s when people realized that. So it's quite new discovery. And once people discover it, stochastic gradient stochastic gradient descent can be parallelized. So now you can parallelize those things. You can compute those derivatives of this function in parallel. And so you can do whatever, MapReduce, you can distribute it, right? You can do it on distributed machines. You can use it, you can do it on GPUs, also parallelize it using GPUs. So that's what basically allowed to build very large deep learning models and train them quickly, stochastic gradient descent. And then accelerated version of it is called Nesterov acceleration, which was developed in the early 80s. So Nesterov developed this basically acceleration technique for gradient descent, and it was lying on the shelf since then. For 20 years, nobody cared about it. And again, deep learning people picked it up, realized it works quite well for those functions. And Nesterov acceleration is kind of a default thing now when we try to optimize those functions. Okay, so theory of it and why it works and optimization techniques that go into that are not new. So people knew that a long time ago. There's not much new of math is happening here, but just combining those things together, combining it with fast computing architectures, that's what. And of course, growth of the data sets, right? So why it's growing so fast in Google's and Facebook's is because they have growing data sets. They have data sets that cannot be processed with more traditional models, and we can process in deep learning, and we can do it efficiently in parallel. So that's all kind of came together. Back-propagation is technique used to find derivative. That's a chain rule applied to the deep learning model. There's nothing fancy about it. It's basically bottom line. We can calculate derivatives rather quickly and cheaply, okay? And we can do it in parallel as well. There's a whole bunch of startups now that try to develop hardware for deep learning. NVIDIA was the provider of the hardware for many years. It was a gaming chip that can do those matrix vector multiplications quite fast. If you look at deep learning, the main operation is this matrix vector multiplication, calculating those affine transformations. So GPUs can do it very, very fast. And GPUs have been using for a while, and now Google is trying to compete. They have what is called tensor processing unit to calculate those things. And anyhow, yeah, there's a whole big market of chips for processing deep learning models. And this is again one silly example. It's basically linear regression implemented using deep learning framework. So something that you basically specify your prediction rule, right? You say it's x transpose beta plus alpha, which is the bias or constant coefficient, and then you specify your negative log likelihood if you're in statistics, or loss function if you're in machine learning. It's basically prediction minus the true value squared and then summed up. And then you basically say loss that backward. So this function, this is automated differentiation. So that's another one of the innovations of the deep learning libraries. What will happen here, this backward function will differentiate this loss function. So I don't have to go and hand type what is the derivative is. And I can have very complex function here. I can have very, very sophisticated function here, but this backward will still calculate the derivative that happens automatically. So that's the beauty of it. And then optimize the step, basically there's one step on the gradient descent towards the minimum. Okay. So those are a few examples on image analysis, and so machines are becoming actually better for some of the tasks. A lot of the applications in medicine, if you're thinking of image analysis, so you saw image analysis for vehicles last time. There's a whole bunch of applications for analyzing X-ray images and all type of images that happen to be collected in medicine. AlphaGo is a good example. It's basically reinforcement learning, and Alex Bine will become a key, so you will see a whole talk on the reinforcement learning. So I will not go into that. So what's wrong with deep learning approaches? We can point estimates from those, so you just get a number. There is no good model selection mechanisms, and there is no good regularization mechanism. And since there's a lot of Bayesian DNA in this room, you guys do appreciate, that point estimates are not good estimates, that you need some uncertainty. There's a whole bunch of reasons about, why we need those uncertainty estimates to build into the deep learning models. So quick introduction. What is the Bayes? Right. We have. So our goal is to incorporate. So theta is our weights and biases of a deep learning model, right? We just call it generically theta, and we have some data set X. If it's supervised problem, then you're going to have input-output pairs observed. And we want to understand the uncertainty about the weights and biases of the deep learning model. So we're going to use the Bayes rule to calculate the posterior of the weights, which is the product of the likelihood. And again, likelihood in the case of regression, likelihood is just going to be difference between predicted and observed times the prior for P. And posterior basically will have all the information that you can extract from the data set given the prior. So there are two steps in this Bayesian approach, right? We have a training data set D, and we would like to build a predictive model. So we'd like to find distribution over Y given the input X parameters and training data sets. We define the prior. We find the posterior, which is the training step, by applying Bayes rule, and then we predict using the total probability rule. Right. So again, this is a standard Bayesian predictive model. There's nothing different, and whether this likelihood is defined by linear model or by deep learning model, the overall math of it stays the same. So you can think of a Bayes predictor basically averages over all of the models parameterized by theta, and here you basically have a posterior with theta, right? So you can think of it as an ensemble model, and the weights are calculated by the posterior, which is calculated based on the training data set. So it prevents you from overfitting, for example, one thing. It allows you to quantify uncertainty in your prediction because your prediction is going to be distribution rather than point estimate. Okay, so what's wrong with this approach? If you ever try to build those Bayesian predictive models, those two things are intractable in the squares, right? So calculating the normalizing constant and calculating total probability requires integration, and integration usually has to deal with things that are not tractable, so product of those two densities is not going to be analytically calculatable, and you cannot use your whatever favorite numerical integration scheme just because those things are super high dimensional. So if you think of using whatever your favorite trapezoid rule to integrate those things, those work. And actually, those things, trapezoid rules don't even work for simple models, right? So Bayesians tried those. It's like 80s type of thing. So people in the 80s tried to use some quadrature rules to calculate those integrals. Even for simple models, they realized it fails quite quickly. And for deep learning models, this is out of the question. Okay, so we cannot calculate those integrals. Okay, so this is probabilistic interpretation of the Bayesian approach. Again, you basically formulate your likelihood. Negative log likelihood is what is called loss function in machine learning. And negative log likelihood is the loss function. So let's look at the approaches that people use right now. So one of the approaches is what is called the variational inference. Okay, so you have this intractable integral. You cannot calculate those things. So the trick you do is that you say, okay, I don't want to calculate the actual posterior distribution of my parameter theta. I'm going to approximate my posterior distribution. I'm going to approximate it by some other distribution. We'll call it Q. Okay, so this is Q. And this is phi is the parameter of this approximation. So I parameterize the distribution Q by phi. And now instead of finding the original posterior, I want to find this phi. Okay. And the way I'm going to find the best Q that approximates my original distribution is by looking at KL divergence, Q divergence, which is one of the measures. There are several ways to get distances between distributions. KL divergence is one of the ways to measure distances between distributions. I'm going to look at this. And okay, so to calculate KL divergence, unfortunately, on the right-hand side, I have the posterior term, which is exactly what I'm trying to avoid. I'm trying to avoid to calculate the posterior of my theta given the theta, and it shows up in the KL divergence on the right-hand side. So I have to get rid of it somehow, and that's what variation inference does. It uses this identity that KL divergence plus what is called ELBO, we'll look in a second what is ELBO, is the total probability. Okay, and this is probability over data set D. And this one is constant. This does not depend on the weight, okay, because we integrate out the weights here. So this one is constant. So which means that minimizing this one, minimizing KL divergence, is the same as maximizing this, what is called ELBO. And always the upper bound on the total probability. The bottom line is, if you don't follow the methods, it's fine. The bottom line is that we can convert the problem of calculating posterior and calculating those intractable integrals to the optimization problem. So again, this is non-convex function, but we have some ways to solve this non-convex function. And this is function that's quite easier to, anyhow, so it's an optimization problem. This is problem we know how to solve. And we can do it in a tractable fashion, so we can do it in a reasonable amount of time.
Vadim, slow down a bit. So what's the virtue of the Q functions here? Why are you using those?
So Q is a function that is approximation to the posterior distribution. Okay. So the virtue of the Q function is that it's much simpler distribution. Usually, it's going to be mean field inference. So it's going to be product of univariate normals, for example. So what essentially you approximate your very complex posterior with the product of univariate normals. So it's a huge assumption. It's a huge assumption. But if you're okay to make this assumption, if you're okay to live with it, and if you think that's usable for your model, you can convert problem of calculate posterior to the optimization problem. Yeah, to calculate this one, you basically have to have a lot of assumption about how Q looks like. I kind of skip in those details, but that's a good question. So yeah, so that's a trade-off. You can have a tractable solution, but you have to have some assumptions about your approximation here. And that's bread and butter for most of the Bayesian approaches nowadays. It's variational inference. And as you can see, there's a lot of disadvantages just because you have to make a lot of the assumptions. That's basically, this is some with technicality that we probably can skip. Let's see. I mean, I'm just saying that we know how to optimize this function, but there's a lot of technicality how we optimize this function, because we have to calculate gradients of it, and calculating gradients is not that straightforward, so there's reparameterization tricks, but I think for the sake of keeping, yeah.
You say you have relatively easy ways to do that. Is that a true statement for the mean field approximation that you're talking about, or is it a broader statement that's true for other kinds of?
No, it's a very specific set of, so what people do, they say, oh, we're going to approximate the mean field, right? So we're going to take it as product meter at normals, and then we can show how we can optimize this function. But the moment you're away from this very simple set of it's not general statement. It's a statement for a very narrow set of distributions. So that's a very good comment. Okay. So I will skip the details how we solve those problems. I want to talk a little bit about dropouts. So dropouts is another way to bring Bayesian into deep learning. So we talked about variational inference. Dropout is another way to do it. Dropout is a very simple technique. So you generate noise. So your D is noise, and you generate, for example, normal noise with mean 1 and some variance sigma squared. And then you take the weight of your ELF layer of your neural network model, and you perturb them by that noise. So what you do, just introduce noise into the weights of your model, and then you do prediction using the noisy version of the weights. And you do it layer after layer. So to implement dropout, you don't really need to modify much your code. So what you do at each layer, you basically multiply your weights by some noise, and you do prediction. And so you basically introduce noise into the parameters. You introduce the normal noise. And you actually can demonstrate that by doing this technique is equivalent to defining this type of prior on your weights. So the prior on the weights is 1 over absolute value of theta. So each weight of your function going to have this prior. So doing this normal dropout is equivalent to defining such a prior on your weights. This is the graphical representation of this prior. Okay. So there's duality between specific prior and type of dropout that you do. Here's another example of dropout called binomial dropout. So instead of introducing normal ways noise, we introduce binomial. So we just draw zeros and ones. This is Bernoulli distribution with parameter p. So it's a coin flip. Okay, and then what I do, I multiply my weights by those coin flips. So what I do, I basically remove randomly weights from the model. So I kind of sparse it out in a random fashion. Seems quite stupid if you just stare at it, right? So I have a model, I have a bunch of weights, and then I flip coins, bunch of coins, and then I basically take a weight, I flip a coin goes head, like throw out, goes tail, stay, head, throw out. So I basically do that to each of the weights of the model. Quite a strange procedure, right? But you actually can show it. It was a paper published in 2012 that doing this is equivalent to specifying G prior on your model weights. G prior is a normal prior with 0 mean in covariance proportional to the Fisher information matrix. And G prior was a big thing in Bayesian predictive models, and still is actually. It's something that Bayesians understand quite well. So again, this is some very nice interpretation that goes back to traditional Bayesian approaches. It's a G prime. And dropouts is another quite popular technique to bring uncertainty into the models. So you can think of it basically running multiple dropout experiments, and at the end you have ensemble of predictions. And you can think of this ensemble of the predictions as the samples from the predictive posterior distribution. So you can sample predictive posterior distribution by doing dropout, and people do it quite often. The main beauty of dropout is that it doesn't require much code changes. So you just need to introduce this line of code that flip coins and zero out the weights according to the coin flips. Yes.
So just to clarify, you're talking about applying dropout during both the training and the prediction.
So we're talking about prediction.
Okay.
Yeah. So during training, there is a trick that you have to use. Yeah. So we're not talking about training step, obviously. But there's one line change in the training step as well. So both training and prediction basically require very minimal changes to the model to drop out, to be implemented.
Is there a justification to this? It seems, I mean, I get that the neural net has been trained. It's going to give you essentially point estimates for fixed input. You'd like an ensemble of outputs. So you're going to get there by telling your model, which has already been trained to, according to some probability distribution, ignore some, certain neurons to get this ensemble of predictions.
Yeah. Actually, during training, what the question? So we have to do something during training as well. So during training, we also zero them out, but then we reweight the remaining of the weights to make sure that the overall sum is the same. So when we train the model, we have to be aware that during the prediction, we're going to use dropout.
Yeah, that makes more sense.
Yeah.
So now you're
Yeah.
training to accommodate the dropout during the test.
Yes.
What's the comparison between the dropout methodology and a Bayesian neural network, where instead of trying to learn weights, you're trying to learn a probability distribution on each?
It's computationally easy to implement. There is no MCMC happening here. It's like one line of code during training, one line of code during the prediction, and you're done. So variational inference asks you to make a lot of assumptions about. You can use MCMC, by the way. So Markov chain Monte Carlo is traditional Bayesian approach to calculate posteriors for those predictive models. People tried it in the 90s. And the claim is that MCMC fails. So in high-dimensional space, and we know in high-dimensional spaces, MCMC, Markov chain Monte Carlo, does not work very well. And people tried it. And I think at this point, it's like abundant branch of approaches. But I think it might be worth trying to actually go back. And if I personally had more time, I would do that. I would go and actually try those MCMC and see why exactly it happens. And if maybe there's, yeah.
Question for you about this. Have you thought about this in a context? I mean, one way to look at these things is it's basically a coding model, right? So I'm just introducing a compression and a coding scheme, right? So when you think about it in that sense, if I'm dropping out these weights periodically and I'm learning the code at the same time that I'm implying the decode, isn't that just a different way of imagining redundant coding?
Yeah. So people, people realize that you can use it for uncertainty quantification later. First application of dropout, right, was, it's a paper published in 2014, I think. Right. And the application of dropout was to regularize the model. Regularize means remove redundant nodes, right, or redundant connections. Yeah. So that's exactly how the dropout came out. You basically, and that's what we talked to you earlier, you build this very complex model, and then you can apply dropout, and you can zero out a lot of the, so you can make it more parsimonious, as statisticians would say, of a model. Okay, but yeah, that's exactly the motivation for the original dropout. But then people realize you can do uncertainty quantification, so it's kind of a byproduct of what you are saying. Yeah. So, and actually, so I'm done here with current Bayesian approach. I want to show a little bit how we use those approaches in our work. Just few examples of those things. So here's one example is we are trying to optimize a simulator. It's a simulation-based optimization. We have a complex simulator phi, and we have observations of the true process y's. Okay, so we observe the true process. In our case, it's traffic flows, so passenger flows on the network. So we observe the passenger flows, and we have simulated and predict those passenger flows. Our simulator parameterized by phi, and the relationship between the observed and the simulated, we have epsilon, which is inaccuracy of the simulator, because our simulator is an approximation of the true process, so that's inaccuracy of the simulator, and E is the measurement noise. So if you take simulator, adjust for its inaccuracy, adjust for the observation noise, you get the true observations y. Okay, and our goal is to calibrate the simulator, meaning that we want to find the parameters theta, so that the difference between simulated and observed values is as small as possible. So we're trying to fit simulator into data set. Again, as you fit statistical model and data set, in case of our work, this is not some linear model, generalized linear model, it's actually a complex simulator. The problem with that we don't have derivatives, of course, of the simulator. We cannot differentiate this function phi. The simulator is stochastic. Each simulation takes a few hours on a fast desktop, and theta is very high dimensional. We're talking about, and again, our high dimensional is not the same as Google high dimensional. So our high dimensional is a couple hundred dimensions. But even when you talk about 100 dimensions, so thinking about solving global optimization problem with 200 dimensional space. So that's the problem that we're facing. So we use Bayesian approach to solve this problem. We want to build a surrogate F that approximates the simulator. Okay? And we want the surrogate to interpolate our simulator at a given location. So we want to build interpolation. And we want our simulator to have some uncertainty built in. So we want to have some predictive uncertainty. We want to say that the value of the simulator, of the surrogate evaluated at some point theta, it follows some distribution conditional on the observed locations thus far. Does that make sense? And why do we need uncertainty in our surrogate? Because we want to have sequential design of experiment. We want to use this uncertainty. It's like an active learning. So when I want to sample, when I want to decide which next point to evaluate my simulator at, I want to know where my surrogate is very uncertain. So I want to have my uncertainty as small as possible. That's how I design my experiment. I sequentially sample the input space. And remember, the input space is very high dimensional, and simulator takes a few hours to run. So I want to be very frugal about how many locations I use to evaluate the simulation. So that's basically a setup. Our surrogate model, I call it L, sorry, it was F on the previous slide. So this is my surrogate. My surrogate is a Gaussian process, and it's a standard approach in it's what is called Bayesian optimization, if you're familiar with this term. So I use Bayesian optimization. I have some surrogate that follows the Gaussian process, and Gaussian process modeled by the mean function and the covariance function. And this is my rule, how I want to generate next point to evaluate. So I define some utility function. And let's say my utility function is that I want to maximize. So L star is my best value so far. Remember, I'm trying to solve optimization problem. So I have the best value so far. And I try to find a new value so that the difference between my best and the new value is as large as possible. Right, so that's my design of experiment part, and the way I do it through basically we'll probably skip the details, but the Gaussian process allows me to play between exploration and exploitation in the areas of large uncertainty. That's why I want to explore. If I know that my model is very uncertain in certain regions, I want to go and explore there. But I also in certain regions I have very good values, so I want to exploit them. And my utility function basically is the balance between exploration and exploitation. And the reason I need uncertainty in my surrogate is that I can do this exploration phase. And Gaussian process allows me to do that. Okay. So the problem with solving those high-dimensional global optimization problems using the surrogates that you have to explore this high-dimensional space. This is a little bit of, again, silly examples of how cursive dimensionality works. So if you have just 20-dimensional space, and you have a simulator that takes 1 second to run, and you want to have a naive design of experiment, meaning that you want to cover the space by grid, and you're going to have 10 points in each dimension in this grid. Very simple design of experiment, very straightforward. So if you cover the space with that grid, you'll have 10 to the power 20 locations on the grid, and even at 1 second per simulation, it will take you 3 trillion years to explore this grid. Okay? So we're talking about 10 points per the dimension, very fast simulator, 3 trillion years to explore the space, and feasible. Even if you want to evaluate the corners, it's to the power 20 corners. It will take you 12 days to evaluate just the corners. Okay, so we have to do something else. And the way we solve this problem is this is the contour plot of the simulation outputs. So this is, we just took 2 variables out of 200 dimensional spaces. So this is theta 1 and this is theta 2, and those are the values calculated by the simulator. And what you can see here, that you can see actually some patterns of those values. You can see that there's a lot of change happens in this direction, and not much change happens in this direction. Okay, so now what we want to do. We want to build a neural network that exploits this pattern in the relationship between my inputs, theta 1 and theta 2, and values of the simulator. And essentially what I want to do, I want my, as you said, I want to compress. I want to build a neural network that compresses my high dimensional space into lower dimensional space while taking care of those patterns in the outputs. So this is my goal here. I want to build a neural network. The general idea is that this is my original theta. So I have compression part of the network. I have decompression part of the network. Idea is that when you combine compression and decompression, your recovery, the signal is going to be as close as possible to theta. So that's, we try to minimize this term. But we also try to minimize this term. This is deviation, so this is compressed version, and this is a surrogate, deep learning surrogate for the predicting y. And we want deep learning surrogate to be as close as possible to true y. So we don't only want to find low-dimensional representation of the input space. We want to find low-dimensional representation that captures relationship to the out space. Okay, so that's it's a little bit weird construct, but it works. This is our model. So we have input parameters theta. We go through compression stage. So we have reduced dimensionality representation of the theta, and this is our part of the neural network that takes it from the slow dimensional to the outputs. And remember, simulator takes inputs to the outputs, right? So that's basically approximation from inputs to the outputs. This is our decompression part of the model. So we take it low dimensional representation and we can decompress it back to the higher dimensions. And now what we do, we build a Gaussian process here in this space. And we do our optimization in this space. And we do uncertainty quantification in this space. So we build a surrogate model that just works in this low dimensional space. Okay. Again, I'm not going to go show results, but it beats pretty much any single naive approach that you can imagine. This compression decompression trick works quite well, and we can bring uncertainty. So we quantify uncertainty on this layer. So what we do is essentially we take this one and we feed it to Gaussian process, and Gaussian process provides the uncertainty. So it's actually not a naive way to, or simple way to bring uncertainty into your model. So you can think of deep learning model basically building your features and compressing your space into low dimensional space, and then you can slap some probabilistic model at the end of it. In our case, it's Gaussian process, but you can take your favorite Bayesian model at the end and just build this Bayesian model on those outputs. So that's how you can go from those high dimensional inputs, and you can still use your favorite Bayesian models that work in low dimensions, and you can ask neural network to compress your inputs low dimensional spaces. Okay, so that's the trick with essentially leaves here. Okay, I think I'm out of time, right? Yes, I'm out of time, so I probably will stop here. Actually, it's a quick example of how this reconstruction works. So I have a 100-dimensional function. So x is 100-dimensional here. I just take an inner product and an absolute value, and I have a univariate function. And if you plot the x0 versus value of x, you basically see some noise. But the deep neural network actually can find this pattern, this V-shaped pattern, absolute value pattern in this relationship, without me telling how this pattern looks like. So it can recover this low-dimensional space in the. Okay, so probably we'll stop here. I'll go to the. I have a few examples of the work that we're doing, but for the sake of time. So in the summary, many successful applications. Deep learning can improve on traditional Riemann Fourier models, and we can compose it with Gaussian process to bring uncertainty into our modeling process. And variational Bayesian dropout is, I think, the first steps towards bringing uncertainty into those models. Variational Bayes is very slow also, and it has very harsh assumptions. So I'm myself not a big fan of the variational Bayes approach. So I think we're still doing baby steps towards the direction of bringing uncertainty into those models. There's still a lot of work to do. And again, this is a crowd that doesn't need to explain why uncertainty is important. We want to use uncertainty for explainability of the model and for policy making, for example, or in robotics applications you guys saw last time. We want robots to be aware of how certain the perceptions are. Right. Okay.
Well, Vadim, thank you very much, and we'd like to have open the floor to some questions.
Well, I have one. Nice question. So, you said early on, and with great emphasis, that Kolmogorov and Arnold said that basically 3 layers are enough
Mhm.
Obviously, you're using a lot more layers.
Mhm.
What's the theoretical justification for that?
So your
Why
number,
bother?
your number of neurons have to grow exponentially in the shallow networks.
Is there theorems?
Yeah. It's actually, well, there's no general theorems. There are a whole bunch of simple examples. So one example was a paper 2016 by Kalgarsky. So what he showed is you take a function that looks like a zigzag, okay? Like just a zigzag function. It's basically a piecewise linear function. If you try to build a shallow network that approximates this function, then the number of neurons in the shallow layer has to be, it's an exponential function of the number of peaks in the zigzag function. And it's a very simple math. It's like high school math, you can show it. And then he shows if you build it in a deep fashion, it's a linear number of neurons that you need to, as a function of those zigzags. So there's a whole bunch of examples like that that show you why you need this direction versus this direction. But I don't think there is a general theory about it. But that's, yeah.
Isn't there a trade-off between the number of layers and the smoothness of the nonlinear function?
I
think so.
Doesn't have to be.
So you need more layers to have if you have very non-smooth patterns. So if you have a line, right? So think about simple case. If you have a line, if you have a linear pattern, then you can just fit the line in it. So it's a neural network with one layer without non-linearity, right? If you have a spiral, so the simple examples I showed, right? Spiral actually require you 2 layers with some non-linearities. So I guess, so intuitive answer to your question is that the more complex pattern, the more non-smooth pattern you have, the more layers you have to introduce into your model. Does that?
Yeah, I was actually asking something slightly different, which is if you fix your multivariate function. What I've been reading, just after being inspired by this theorem that I had never seen before. The result seems to be that if you reduce the number of layers, then the nonlinear functions that you need to apply are increasingly non-smooth.
Yes. So that's actually a result. It's also a result from late 50s. I cheated a little bit. So I told you it's Kolmogorov-Arnold and then showed you something smooth. But it was actually shown in Kolmogorov-Arnold formulation. Those nonlinear activations have to be non-smooth. Even if your function f is smooth, you're trying to approximate. Yes. So Kolmogorov-Arnold is not a very applicable thing. It's just a concept that gives you a warm feeling about the whole idea of building those superpositions. But it's, if you try to actually implement Kolmogorov-Arnold, one thing you have to have non-smooth activation functions. And those the way to build those activation functions is basically infinitely dividing the input space. So it's not very practical. You cannot build algorithms around this concept. But yeah, there is non-smoothness in Kolmogorov-Arnold. Activation functions.
What developments have occurred since the 90s that make you think it would be interesting to revisit MCMC as a way to generate posterior?
Why don't you try to repeat the question?
So the question was, what happened since 90s when MCMC was tried for deep learning? Well, my concern is nobody else have tried it. Maybe people tried and never published it because it really doesn't work. But you basically see this publication in the 90s. People claim it doesn't work, and then it disappeared. So, what happened? I think not much actually methodologically. So we have faster software now. We have different MCMC flavors. So in the 90s when we had whatever Gibbs and Metropolis Hastings. So now we have this derivative-based MCMC. So but it's actually not that great of improvements. I don't have a good feeling why. But it seems like wrong, right? People tried it in the 90s. Nobody came back to it afterwards. Somebody claimed it doesn't work. And I think what happened, actually, people who claim it, Rathan Neil, he's a very authoritative person, right? From Toronto. So he has a lot of, people put a lot of trust in what he says. And I think so much. So part of it, what happens is like, oh, person who knows what he's talking about said that, so we're just going to leave it alone. And, but I think it's still worth revisiting and trying it. Yeah, but just a very strange, I don't have a good explanation why people should.
I mean, expanding on what you said, I mean, we sorted through the talent on neural networks in the 90s anyways.
Yeah.
So what changed to make that work?
Yes.
Same topic, right?
Yes.
Lots of compute. And so, yeah, why does MCMC take a long time? Well, I got to compute a lot of stuff. So does it make a lot of sense to go back and look at what you can do with today's computing environment? And maybe some new tricks, MCMC tricks, will come out of, if you try to approach neural networks with that, So, yeah, you're right. Perceptron was kind of abandoned for 30 years just because Minsky said it doesn't work. And it was the same story. It was a person with a lot of authority, person very well respected, wrote the book, said this thing doesn't work, and the whole research community abandoned for 30 years. So I'm afraid something similar might be happening to MCMCs. I don't have a good, yeah.
So you have this general technique, it looks like, where you use an autoencoder, you get to a smaller dimensional space. So it seems, I just wonder what kind of analyses that maybe don't work at high dimensions can you do in low dimensions on your low autoencoded space, and then blow them up again to get something you can actually use.
So you mean besides our global optimization?
Besides your global optimization, yeah.
Okay. Well, we might be thinking of building some Bayesian models that require MCMC, for example. And again, MCMC does not scale well in high dimensions, so you might want to build set of features. Let's say we can talk about simple Bayesian linear model, hierarchical Bayesian linear model, right? Some complex priors. But then the question is, because usually when you put your prior on the parameter of the Bayesian model, usually you have some like it's a sparsifying prior, right? So you put Laplace prior so that you can zero out a lot of the parameters of your model. When you move to the feature space, what do those priors really mean? And it's yeah. So I haven't thought much about it. What else you can do? But it seems like wherever there's computational difficulty working in high dimensions, in our case, it's a global optimization problem. Yeah. I don't think I have a good answer. Sorry.
Okay, so this concludes the talk. There'll be a little bit. Don't go. Don't go too far. Don't go away quite yet. There'll be a little presentation afterward. Stick. Anybody that wants to continue the discussion, please stick around.
Are we going back after lunch?
Yeah, and there'll be after lunch. Vadim will be back until about 4 o'clock for further discussions for those that would like that.
Back here. We're just back. Metro. Yeah.
The only place that matters is Metron.
Yeah, right. Yeah, right.
So let's start off there.
Okay.
Vadim, I want to thank you for coming out. I think it sort of speaks to the interest in this that you've exceeded the capacity of our room, at least in terms of the furniture. So the good news is the furniture order comes in this week, so we'll have more chairs next time around. But